the assembly of the timber elements, and this assembly is then completed with metal elements such as screws and tie rods. Then we have the timber frame buildings, which we often see depicted in American movies. Well, these types of houses are present in Italy too, even though from the outside we cannot tell that it's made of wood. For example, at the top left corner we have no perception that this house has wood.
Considerare il legno come un materiale che sostituisce gli altri elementi portanti, che siano mattoni, calcestruzzo armato, acciai, eccetera. E non è detto che sia a vista. Questo è un esempio di edilizia fatta coi pannelli detti X-lam o cross-lam, correttamente in inglese sarebbe cross-laminated timber, e qui è un'edilizia un po' particolare perché siamo all'Aquila in edilizia.
Of a building. This is a post-earthquake building in l'Aquila, and there is a lot of technology behind this type of work. So you can see pressuring of the panels. They lend themselves very well to rapid assembly, fast assembly, and prefabricated buildings. Solid wood cross-lam timber buildings are growing in numbers, and they are very important because they contribute to CO2 sequestration, which is fixated by trees, and it stays in wood until that building is demolished. And it is also important because it all allows a better sustainability, especially if compared to concrete, steel, and so on and so forth. So we may discuss whether it is more or less impactful, if it is more or less sustainable, a wood timber-based material versus another. But if you compare wood or timber-based elements with other construction materials, for sure timber has a higher degree of sustainability, and this is certainly a very important incentive for whoever needs to make a choice in terms of which material to use for structural use. I may now be a little bit boring, but I'd like to hint a little bit at the construction rules, technical construction rules. The latest edition in 2018 has somehow changed the approach by planners, by designers, the approach that they had to wood. The arrival, the introduction of these rules allowed timber to be on the same footing as the other construction materials. Before the publication of these rules, we had to come up with somehow different arrangements. We had to make reference to international rules or to established habits and practices. But then in 2018, the technical construction rules were released, and from that very moment, wood has acquired the same dignity as the other construction materials. And of course, this also implies equal obligations as other construction materials. So it may sound a little bit strange or odd for me to pay attention to this legislation, but as a matter of fact, it was a long path to be completed. This allowed Italy to arrive to an adequate legislation framework. It all started back in the 80s when Europe tried to put together common and joint calculation rules like Eurocode 5, but that was only on voluntary basis. Then a commission was set up in Italy for technical construction rules. It went through a sort of a standstill for a certain amount of time, and then they released a version of the first version of the technical construction rules in 2005, and then it became mandatory to complete structural calculations for buildings, and the final version released in 2008 became effective in some years later, and it was then updated in 2018 when it was revised and updated. And in 2009, the guidelines on understanding the technical construction rules were also developed. So I will not go through every single pieces of the construction rules. The focus on timber is in Articles 4.4, 7.7 and 11.7. And our focus will be specifically on 11.7, so materials and wood-based products. This is the chapter that we are going to pay attention to, the 11.7, because this chapter defines the requirements of the materials properties, procedures to qualify materials, and this means that all the rules and regulations for construction materials are set and are mandatory to be complied with, including wood, including timber. And this is important because in the past everybody went their own way. There were no rules, there was no regulations, first quality materials. Everybody, different materials were qualifying as quality materials. So it's important to have this set of rules that allow us to build safely. Chapter 11 of the technical construction rules also identifies the important professional profiles for the building process. Producer, the manufacturer, the planner, the builder, the construction site manager, site inspector, and so on and so forth. Each professional profile has its own functions described in the technical rules. Also in terms of choosing the correct quality of the materials, be it solid wood or lamb wood. And of course these requirements must be verified, assessed and accepted by the construction site director. So timber and timber-based products therefore are required to go through the entire legal requirements as any other construction material. So any product based on timber or products derived from timbers, be it panels, trusses, beams, they must be identified uniquely by the manufacturer according to specific procedures. They need to be qualified. They need to qualify to be qualified by the manufacturer. This means that the manufacturer needs to indicate the grade of the material, the quality of the material, the structural quality, the structural properties like resistance or supporting capability. And these data must be specified in the project, in the building project. They must match, and they must be accepted by the construction site director. There may be some problems here because sometimes the construction site manager is used to work with steel wires or concrete blocks, and when they receive timber-based elements, they send it to the laboratory for testing, and maybe they don't realize that wood is not concrete is not steel, and it's not been made by man but by nature. testing laboratories throughout Italy receive pieces of timber taken from structural beams with the request to run tests that make no sense at all. So a laboratory would have to point it out, so you cannot run this test with the timber. Some other laboratories decide to just be paid for that, but without providing any added value for that kind of test. So this is a very important, relevant aspect that is somehow being discussed, and we're trying to solve it from a regulation point of view. So sometimes we have planners that are working for the very first time with structural timber. So basically, the rules need to give some warranty to the end consumer. This was the purpose of the Eurocode 5 and also of the technical construction rules. So basically, we now have a system which allows us to ensure the quality of what we build, allows us to trace the materials and their manufacturers from the very time the material leaves the factory to the time it is implemented and used in the site. And that's where the marking process steps in. We're used to say that a roof tile has a mark, has a brand or a mark stamped on it. Well, we need to get used to see marked logs or solid wood beams or trusses. This brand or this mark that is applied on the structural element allows to make a quality leap when we trace back the entire manufacturing pipeline. So the marking must be unique to the company, to the type of material, characteristics and properties of the material, and then it should be accompanied by the declaration of performance and by all other documents that allow the planner to be confident that he's working in full safety. This is a picture, unfortunately, that comes from the UK. As of now, I have only rarely seen in Italy the marking of strength, class, and the other properties in Italy. But this comes from the UK. In some cases, the marking is made with hot pressing procedures, some others with ink, and based on this EC marking points, we can retrieve all the key pieces of information for our material. So key pieces of information which will be the focus on of the next part of my presentation.
Now labeling, and unfortunately in Italy, in spite of the fact that technical rules provide for wood to be labeled, however, there are possibilities of non-labeling wood elements, but accompanying them with a document summarizing the characteristics of the wood provided. And what is an exception in Italy has actually become a rule, because oftentimes, for financial reasons, you prefer to enclose the document rather than marking and printing the individual product item. They just say that you spoil the beauty of the beam, but that the marking is usually placed somewhere where you don't actually see it. But we should get used to the fact that marking is something that is also important for us, because we sleep on it. So let's move on to talk about structural wood, or wood for structural utilization. It's always important to understand that what we see in this picture is our plant, production plant. This is where we produce hardwood. In these two woods, that are on a plane almost. Instead, we are producing softwood. So our primary manufacturing plant is the woods. And this is a big difference, especially in relation to the fact that our material is growing as nature lets it grow. As you see on the left-hand side, it's two chestnut trunks that are presumably two children of the same strain. One is perfectly straight, whereas the other one is all but straight, so cannot be worked. So you understand that we're dealing with natural raw material, grown up according to the laws of nature. The environment, the weather, the fact that there was fire, it's a windy area, worms, fertile soil. And this does imply an enormous variability in characteristics. If you then multiply it by the great variety of wood species that are available, you have a number of characteristics that can vary, so it's extreme variability of raw materials. And if you talk about steel, I decide how much iron or carbon I want to put in it. If it's concrete, I decide the amount of sand or whatever, but it's different. If we then take a close look at a piece of wood, this is macroscopic enlargement, you can see the strength of this raw material. So in this piece of fir, and spruce is no different, there's much more air than wood. So if you take a piece of wood in your hand, that thing that looks solid, it's made of 2/3 of air, so vacuum, empty space. 1/3 is cells, cell walls. That's where we appreciate, where we get the characteristics we appreciate. It's normally ice insulating, thermally insulating. It's lightweight, so it's good for construction in earthquake regions. Unfortunately, we used to materials that are made. I mean, this is for concrete again. We used to have concrete iron and saying this is good, this is no good, this works well, this is broken, this less concrete, more concrete. Whereas nowadays we have a different situation where our first material is made of wooden elements, and in a rack like this you won't find two pieces of sawn timber that look exactly like another, because the rings, how it was sawed, the defect, the knot, you won't find two pieces of sawn timber that are the same as the other. So then a house designer will tell you, well, I can't do this. How can I use different pieces? How can I be assured that the two different beams hold the same? I tell you how I can do it. In order to solve this problem of natural variability of wood, Europe has defined a principle that allows us to reduce this natural variability and make it contingent, so to really reduce it significantly, to reduce exactly the possibility of having different values for our material. You see here two charts, real beams, spruce from Val di Fiemme in northern Italy, 215 beams. And you have the values here. I won't go into the details, but the average strength value is 44.6 megapascal. The characteristic value is 254 kilograms per square centimeter. So if I take it like this, I have sawn timber that break at 120 kilograms per cubic centimeter, and others that break at 700 kilograms per square centimeter. So our goal is to reduce this variability, to select timber in a homogeneous group. It was, again, 215 beams. It was, and each piece of timber broke in its own peculiar way. And if we transform sawn timber, any kind of sawn timber, into a structural product, we have to go through selection. We cannot produce solid wood ourselves. It's made by nature. We can only saw it from the tree. Once it's sawn, we can select it on the basis of its strength characteristics. And its strength properties are the ones that affect the resistance and strength of the beam once it's in place. And again, visual, that's where we talk about visual or machine grading. We get the sawn timber. It is sawn timber is classified. Each piece is graded, and some pieces are actually discarded. This is a total new way of working. In the past, they would sell you timber as it was in bulks, whereas now manufacturers have to grade sawn timber one piece at a time and discard, get rid of the ones that don't comply with minimum requirements. Now, solid wood, so switching from sawn timber to structural wood, nothing changes in terms of the product. The one above is any type of any timber. The one below has been selected to be structural wood. And this applies also to lamb wood, and it applies to cross-lamb timber. So each board has to be graded, otherwise it's not structural timber or wood. So this was the introduction. Now I'm going to briefly summarize, give you an idea of how the principle works. So we're going to talk about visual strength grading. Here too, many designers were a bit skeptical about this, telling me, you give me parameters, recommendations, but actually, who knows wood? And knows wood since when wood was a tree, and so knows the characteristics, properties, defects of a tree that actually become the properties of wood, knows all of these properties and characteristics, especially the ones that impact on its strength. So here it said that the rules say that grading criteria ensure minimal mechanical performances that are statistically determined. So we basically establish characteristics that are statistically determined so that we know the risk of using one value or another, one grade or another, without the need for additional testing. We define the resistance profile or strength profile, so the set of mechanical properties of that wood. If I get C24 class grade wood, I know what, I mean, it tends to stiffness, strength, flexibility, bending, all of the typical characteristics that structural wood must have. And a category, so grade, is assigned to wood that defines its quality, but it's not the quality that we decide subjectively. It's certified quality with references to the wood species and with reference to the geographic location. And what does geographical location have to do with this? It's just spruce, but I can tell you that spruce growing on the Alps, looking onto the Po Valley, low altitude, high altitude, it's different. Spruce growing in Germany does have different characteristics other than spruce growing in Italy. So geographic location does have an impact. And then wood belonging to a specific category is assigned a specific resistance profile. The designer goes to the specific strength properties. So the designer, the architect, defines the properties of wood that he wants to have. So the designer C30, so I must give him wood that is C30 graded. So this is an example of different visual strength grading: Italian, Swiss, German, Scandinavian. So with a number of established criteria. Some criteria are law requirements, and we're talking about European regulations. The harmonized regulation by the EU that establishes the minimum requirements to ensure strength, wood strength. Then the measuring of knots is done differently in the UK than with car. No knot area ratio. In Germany we have the minimum knot diameter. Everybody has got their own criteria, but when there is specificity we can identify an additional criterion, but the minimum criteria are assured and guaranteed by the European standard. There are countries that have been grading for 100 years, and we Europeans could not go to them and say, now you're going to use the EU regulations. So everybody actually developed their own national rules. And in Italy we have UNI 11035, which was released with updated just recently. So it's timber. So it's visual strength grading of timber, part 1 for, so it's part 1 for softwood and part 2 for hardwood. And this is a very compact release. So we have everything in one single standard. Just a few examples, we won't go into the details. The Italian standard, UNI standard, somehow aligned to the German standard. It's not really like Germany, but basically in the 80s and 90s a number of tests were made on Italian wood, comparing, and thereby comparing different European laws, I mean national laws. We didn't have the EU regulation, so we compared the rules from Germany, Scandinavia, Switzerland, UK, and the German system, standardization system, was the one that allowed us to obtain the best result with the least effort. So somehow the Italian standard was similar to the German one, and here you have knots, you have individual knots, clusters of knots, and so they are assessed and measured if they are of a certain size to make sure they comply with the standard. An expert grader knows, doesn't need to know if the knot is 25 or 27. He just needs to know if it is below 20 or between 30 and 40. So you don't go there with a ruler to actually measure, but it's just visual. So you measure where you have concerns, where you are, I mean, for instance, if a knot is below 0.4 or 0.6, for instance, to know whether it belongs to one class grade or another. Because knots don't have a value in themselves, but they do have a value in reference to the zone Tiber where they are located. So if I have 2 centimeter knot on a 30 by 30 it is one thing, whether I have a 2 centimeter knot on the same beam. So knots are the first criterion that is considered when doing visual strength grading. Then there are additional parameters, the slope of the grain, for instance, those vertical tubes. If you're lucky, they're quite straight. Otherwise, they're a bit sloped on the edge of the zone Tiber. The width of rings has to be measured, especially for certain species, because if wood grows slower, then it's thicker. Like a pine grown in Sweden compared to a pine grown in central Italy. So the width of the rings is an important parameter, and it does have an impact on the density of wood. Density of wood is important in mechanical connections, screws, pins, bolts and nuts, everything that is metal and has, and metal is much more rigid than wood. That they have to do with the wood. So we need to measure density to know how it will resist. Then some defects, because chestnut, for instance, is a typical Italian wood, which does have a typical defect, which is ring shake, but in our standard we do allow for ring shake, because we do love chestnut in this country. Visual grading with the Italian standard 11035 applies to these 7 species grown in Italy. So softwood, fir spruce, Douglas fir and larch, hardwood, chestnut and beech. Beech is new because it was introduced in the release of April 2022. So now these are the wood species that are grown in Italy that can be graded and marketed for as structural wood or wood for structural use in the construction industry. I'm going to invite you not to. So hardwood, we're talking about hardwood, and it's in Italian is not translated literally. So I have to, I'm a university professor, so I have to point certain things out. However, hardwood. So how is grading standard? This is for fir spruce, Corsican pine and larch. There are some, it's a bit small print, but second line, there are characteristics having an impact on strength, and it's knots, rings, grain, fissures. Why? Does lane have fissures? Yes, it does. We get called so many times, but the lady just back from vacation, middle of the summer, the beam is collapsing, there's a fissure here. Well, fissures are a rule, basically. And it's right normal that you would have withdrawing fissures or shrinkage fissures in wood, especially construction wood used for beams. And these are 4 parameters having an impact on mechanical characteristics. Then we have geometrical characteristics. So we have veins, so there's a lack of wood, and deformities that do not have any impact on strength, but do have an impact on assembly. If there's no leaning for the wood element, of course, that does have an importance. And then there are additional characteristics like biological attacks that are not accepted in most cases. And then the rule also requires provides for 3 categories, S1, S2, S3. So in Italy, FIR S1 is class C30. So designers use it for grading class C30, 300 kilograms per square centimeter. And it's not the average value, this is the minimum value. S2 is C24, 200 kilograms per square centimeter. S3 is grade C18, so 180 kilograms per square centimeter. So designers can choose among these 3 grade strength classes. And then we have softwood 2. We have Douglas fir, which is an American wood, Northern American wood, which is actually taken over in our woods, in our mountains, and it does have beautiful strength properties, and it does maintain high performances, high density. So we dedicated a rule, a standard specifically to Douglas fir, so S1 and S2 grades. We move on to hardwood.
La regola sta cambiando.
Well, the standard is changing, and shortly there's going to be the European standard EN 1012 that associates or relates categories to strength classes, species to strength classes. So the next, so 1912, the number. We'll have 2 possibilities with Douglas fir. If I grade it into S1 and S2, I will have C22 and C30 respectively. If I put them all together, so just S1, S2 is better, so it's beyond, so it's all C24. So it depends on how the manufacturing plant is set up. If they want to have C24, it's just S2. If they want to do more, they can differentiate, but they cannot have C24.
Il procedimento.
Well, the procedure is by which we do assign value to structural wood properties, so it's different. So if I establish threshold values for S2, I'm able to obtain better gradings, so I end up in C24. But if I do have S2 and S12, part of the better material does not help me to contribute to S2. If I split into 2 categories, S2 is C22 and S1 goes into C30.
220 kg.
220 kilograms per square centimeters. That's C22. The characteristic value is the minimum strength value, threshold. Then we may have sawn timber that supports much more than that value, but that is the minimum requirement for the planner. So if you take Douglas fir, it not only bears 220 kilograms per square centimeters, even more. Let's finish with chestnut, which only has 1 category, 1 class, LS. It ends up in D24, 240 kilograms per square centimeters, and then we have the new rules for beech timber. Beech timber doesn't have a market yet. It has 2 categories only, LS1 and LS2. We are ready for the future developments. In the future we will have other timber species, other wood species, and we will try to implement the number of species to be used for structural use. So LS1 and LS2 is what we have now available for beach. I can't remember them well by heart. I may be wrong, but I think that LS2 is 30 and LS1 is 35. Beech wood is much more resistant, stronger, but it's also more dense. So the density of chestnut is 580, spruce 420. So the more wood you put, so more walls and less empty spaces, it bears more weight. But again, I don't remember all these classes by heart. I need to double check these values. There is a question from the audience which we cannot translate because we didn't hear it. For oak timber is not yet available in Italy. There is no visual strength grading rule in Italy. So whoever buys oak wood, buys it from the international market, not in Italy. In order to give you an idea, in order to determine values, we need to break some thousands of samples because we need to work on large numbers. The value thresholds need to be determined statistically. So from going from timber to structural timber, the difference is the grading and the fact that we need to discard some materials. In the graph, the big curve has no piece in the lower part of the graph. That is the material that was discarded, that could not be classified as structural use. This is something we need to bear in mind. So there is a certain percentage of material that must be discarded. I only have 9 minutes left, and I will focus the rest of my report on machine strength grading, which is the innovation, and it is the reason why I'm here. We have machines here, we have manufacturing machinery. So next to visual strength grading, we also have the machine strength grading. This table here was designed purposely to compare the two grading principles. Let's look at the benefits and disadvantages. The bold character indicates advantages, benefits, so more productivity, hundreds of pieces per minute can be graded. There is a possibility for automation, so you can, there is excellent repeatability. Two grading processes on the same sawn timber piece allows me to have the same, to end up with the same strength class. Several diverse strength classes and also better yields from a quality and quantitative point of view. On the other hand, visual strength grading costs much less. It is within the reach of small companies, and in Italy we are faced with a market characterized by small and medium enterprises which cannot afford a 300,000 euro machine. It is available for different wood species, and it's easy to switch from one wood species to another one. So now we have a fir, and that's now switched to birch. It's more versatile. But on the other hand, there are some cons. So it produces much less in terms of quantity, and then it's operator dependent. So the grader grades in a better, worse way, so less predictability. So for categories, for classes, chestnut has only one category. All the rest needs to be discarded. We tried to establish two classes, but values did not allow us for two classes. The values were too similar. The lowest class and the highest class were pretty much similar, so it made no sense to distinguish these softwoods, these hardwood species in two classes. We only have one. So what are the grounding principles for machine strength grading? It's based on non-destructive methods. So basically a selection of parameters are measured. These parameters are related to stiffness and resistance. So these machines measure different parameters. They're put together, and based on a statistical collection of data, we then grade the various sawn timber. If they're not good, there will be a pile of discarded timber, which will be sent to carpentry for other uses. But it must be a separated, segregated pile of wood, not to be used for structural purposes. Let's now look at some of the principles that we use for wood board grading. There is a system that we took from the Nordic countries, and it started from the bending principle. So we take a wood board, we bend it on the flat surface, and we see how stiff it is. So the stiffer, the more resistant to cut it is. So the board goes into this machine where it is flatwise bent, and based on the point where it is most bent, that's how I would grade and classify my board. And I will print the abbreviation, the acronym of the class there. This is one system. Nowadays, there are new methods that are much more versatile, faster. So the dynamic systems. These dynamic systems are based on the free vibration of the sawn timber. You can see this small machine, MTG timber grade. We have it in our university department. You can use it on small lots of production from 120 boards per minute. So one board every half a second. So it's faster, it's suitable for production lines. Well, there are also some other manual grading systems, ultrasound based, some other devices used in laboratories, and pressure waves. The principle is you need to vibrate to get a board to vibrate, and based on the density and the frequency of vibration, which basically means sound, the board will be more or less stiff than another. And based on the stiffness, you can then establish the connection, the relation to strength or resistance. So this system turned out to be very, very efficient. How is it? You just get a board to sound, and that's how you grade it. Exactly. So you can take a sawn timber piece, just hammer it on its head, and you get a sound, a perceptible sound, and you can regulate it. And based on the sound, you can grade it into a class. There are also much more performing methodologies, combining X-rays, optical inspections, X-rays, a very, very complicated methodology. We also are lucky enough to have a Microtech in Italy. It's a company in the province of Bolzano, northeast Italy, sells worldwide, and it has very accurate, reliable, dependable, and valuable, accurate classifications. And here are some of the grading machines. These machines, this is a list of strength grading machines. So Kukubo, Linderstech, Mac, Grade Master, Golden Eye, Eurograde Comet, Golden Eye, VM Grader, Dynagrade, Rotating Grader. There are many machines. But on the Italian market, this type of process has not taken roots already. So many companies haven't digested yet the process. But it would be very logical to have a production line of sawn timber and have a grading machine attached to it and sell my sawn timber for structural use. This is the principle. I will take the non-destructive parameter on the horizontal axis. I will correlate it to the strength of the material, and based on how good this this relationship is, I can then establish the threshold value which drives the grading of the sawn timber. If all the values are close to the median line, my correlation will be very, very good. So I will calibrate the machine below, so that below that value is my sawn timber graded for structural use. If the distribution of values is less efficient, it takes the shape of a cloud, like in this case, then my machine's parameters will have to be calibrated to a lower extent in order to be sure. First thing is safety. So this is the basic principle. I will not comment on all the data. Here what you see is knots, either measured with machines or by visual grading. The relation with the strength can also be obtained by a combination of parameters, a dynamic value with the number of knots, or density with the number of knots. By doing so, you can improve your grading results. So the more scattered the clouds are, or the closer they are, well, that depends on how you combine different thresholds. These are values attached to the sawn timber that I broke myself in that Trento Carpenter's workshop. At the bottom on the left, you can see more compressed values. We combined more parameters, knots, vibration, and density, and this improves greatly the ability of the machine to grade properly, and therefore the possibility to obtain rather good, fairly good strength classes. This is experimental data. I will not reveal when I did this many years ago, but this is the principle underlying the whole process. Of course, today's machines are based on today's actual number, but these were experimental data. I had them available to show it to you, and let's see how they interact with the machine grading process. The combination of values on the left are alternative scenarios. So you can obtain C40, C30, C18, which you cannot obtain with the visual grading process. Or if you want to maximize, you can get all to C24. So based on my choice on how to set up the grading machine and based on the tests, I can then obtain different combinations that are more or less suitable to my purpose. Maybe I want a niche product, a C40, that a certain client may require at a certain given time. And I have this possibility. So the grading yield is much better with the machine, and of course the grading classes are much higher. In this exercise of mine, I showed how the different classifications could be different from 70% to 75%. That was a very small batch, experimental lot. And this same principle should be implemented and applied to modern systems, to modern machines. And my very last slide. So timber building, timber construction industry continues to grow, not only because Europe asks us to do so. This is an expert from a speech delivered in September 2020. Prior to the war, and so we still thought differently. But wood construction industry will not save the wood, but can certainly greatly contribute to reduce the greenhouse effect. And so we need to convert our production systems towards that direction. Timber-based buildings are less demanding, both in the face of production, and they can also be more sustainable if compared to buildings made with other materials. Especially if we look at, let's say, massive buildings. Here we have glulam buildings or X-lam buildings. These are solid reservoir of CO2, basically. So until the very moment you demolish that building, and it must last at least 50 years or even 100 or 200 until your decision is made to demolish it. Well, until then, that CO2 amount is tied up in there. And this is the major difference between timber and the other construction materials. Let me now close my contribution. I know I extended a little bit my available time. If you have any questions, I am open to take them whenever you like, individually or jointly or together. Thank you.